Welcome to the third unit of the second week in the Parallel Programming Concepts course. My name is Peter Tröger. We already talked about the notion of concurrency and parallelism when we actually target parallel programming and parallel software development. In this unit, we want to look into different concepts, fundamental concepts that are used in order to deal with the race condition problem that you may get if you have concurrent execution in your software. Concurrency, as I already explained in the other unit, is a classical operating system topic, so it has a long tradition. A lot of theoretical and practical research happened in that area. And if you now try to go back in time and try to understand where did this all start, we have two examples here what are relevant landmarks in the history of concurrency. So one interesting mark may be the Atlas computer from '61, which was the first one to use interrupts in order to simulate the concurrent execution of multiple programming. So this is one of the first documented examples for an actual implementation of multi-programming in a general purpose machine. The other landmark that may be interesting is the Cooperating Sequential Processes publication by Edgar Dijkstra. In the last unit, I already explained that Edgar Dijkstra identified the problem of race conditions. This was part of this paper, but despite that, he also actually offered the solution to the problem. So he was the one introducing basic concepts such as critical section, mutual exclusion, fairness, and speed independence. So this is a very, very relevant paper. We will give you a link to the publication on the recommended readings list, and I really encourage you to have a look. It's well written and interesting text, and you see how problems identified in the 60s are still valid and crucial today. So one side note here is that if you look into related work about concurrency, you often will find the notion of processes. While we are here talking about concurrent tasks, historically, often people use the term process in order to describe a concurrent activity. You have to accordingly map the terminology when you start reading other sources. Okay, so what was the content of the paper of Dijkstra, of this Cooperating Sequential Processes paper? The overall argumentation line, meanwhile, hopefully sounds familiar to you. So we start with a sequential task, with a single task in an application, and we look on it and we try to understand what is the behavior on a particular piece of hardware, and we recognize that the result of the application and the semantics of the application are actually independent from the speed of execution. This is a good thing. This is something we want to have. So you can take the same program. If we're able to port it from a source code point of view on a new hardware, then we can just run it again. And the execution semantics, the behavior of the program will not change. It will remain the same. If we now take the concurrency example and we have multiple tasks, we again have the situation that we have multiple sequential activities running concurrently. We get some interleaving on a machine that has only a single execution resource, a single processing element, and the speed assumption still should hold. So we want to have the same situation and the same idea that the speed of execution for the different sequential activities should not influence the overall application result. If this is happening, if we have a situation where the speed of execution of the concurrent activities and the resulting interleaving bring different results for the application, then we have something that is called by Dijkstra analog interferences, or in other words, a race condition problem. Dijkstra proposed to solve this problem by identifying so-called critical sections in your code. A critical section is a part of your application execution stream where you want to make sure that only one of the concurrent activities should be inside this critical section. The understanding here is that the crucial access to shared resources, where the interleaving brings us a bad effect, does not happen all the time. We saw that in examples in the last unit, but there are several instructions where actually the access order to resources has semantics, where this is important for the overall application result. And these are the parts in our concurrent application we want to protect. So a critical section is a section in a concurrent program where the different sequential streams of instructions somehow start to overlap, and we get a dependence on the interleaving. And in this part, therefore, we want to make sure that there's a precise ordering of activities as we write it down in our code. Dijkstra already proposed to implement such a critical section by the notion of shared variables. So he targeted shared memory systems or any representative mechanism that allows us to share information. An algorithm that implements the critical section mechanism that allows us to define critical sections has to fulfill a couple of demands or properties. They are widely described in the literature. Here's a short summary about them. The first demand is obviously the mutual exclusion demand. So only one task at a time should be allowed to be inside the critical section while the others are waiting until this one task is getting out of the section again. Then we have the progress demand. So we want to make sure that if no other task is in the critical section, so some activity could actually enter it, the decision for entering should not be postponed endlessly. So at some point in time, there must be a decision that, okay, the critical section is free, you can now enter. The second part of this progress demand, of this formal progress demand, is that only waiting tasks should be part of the decision. So whatever happened inside, the decision who is next should solely be based on only the ones that are waiting on the entrance of the critical section. The third demand on a critical section mechanism is the so-called bounded waiting demand. So we want to have an overall upper time for the waiting. Regardless of the fact whether we have an activity inside or not, no thread, no task should be in the situation to wait endlessly in order to enter the section. This targets obviously the starvation problem described in the last unit. The solution for the critical section problem, for implementing such a mechanism and for having an algorithm that allows us to implement this behavior and to fulfill these three demands was first solved by Decker with his algorithm for two activities, concurrent activities and shared memory. Leslie Lamport generalized this with the bakery algorithm, and both solutions were basically software algorithms, abstract software algorithms, relying on a couple of fundamental assumptions. One fundamental assumption was the atomicity of instructions, so that you have a situation where you really can make sure that one instruction line is executed at a time on a processing element. The second demand was a predictable sequential execution. So they assumed that one line of code is executed after the other. When you now reflect what we have learned in the first week, you will see that these assumptions no longer hold. So we have the situation that due to instruction level parallelism and different optimization techniques in hardware and compiler software, it may happen that the code you write down is not executed exactly in that order. Or it may happen that single source code instructions, for example in C or in any other language, are now optimized by instruction level parallelism mechanisms under the hood inside the hardware, and you no longer know how the access to shared resources is actually happening in real life. So on today's system, due to the heavy optimizations taking place in compilers and hardware already, we can no longer rely on pure software implementations of concurrency mechanisms, and therefore all concurrency implementations today work with hardware support. In modern processors, you have special mechanisms, special instructions such as test and set, compare and swap, and these special instructions now allow you to ensure atomicity on the lowest level, on the processor hardware level, and based on these mechanisms, the operating system now can offer you standard critical section mechanisms to be used. So the general message or the relevant message here is that critical section mechanisms and protection mechanisms are implemented on today's systems by the help of the processor hardware. This leads to the fact that they actually have to be offered by the operating system, and this leads to the fact that whatever you find in user land, in user mode, in programming languages and libraries and high-level abstractions, it actually at the end boils down to mechanisms you will find in the operating system that deal with concurrency and synchronization of concurrent activities. Going back to Dijkstra in the original paper, he's defined a fundamental concept in order to deal with the issue of race conditions and critical section protection, and this is what we call a semaphore. The semaphore concept defines that you have a special purpose integer, so you have a variable, a numerical variable, and you have two operations acting on this variable. The first operation is the weight operation, and this weight operation decreases the value of the semaphore variable by 1. This decreasing is an atomic activity, so nothing else can happen in between, and this is done when the critical section entrance is requested. The weight operation is defined in a way that it blocks if the value of the semaphore variable is already 0. So the idea here is that whenever you try to get into the semaphore, this counter is decreased, and after you finish with the critical section, the semaphore is increased again. This increase operation at the end of the critical section is done by the signal operation, so you increase the value by 1, and this leads to the fact that maybe some other waiting activity stuck in the wait call now gets a chance to again decrease the counter so that it can enter the critical section. With this concept, which is called a counting semaphore, you can set an initial value, like n, and can therefore define how many concurrent activities you allow in a critical section. So if you do, for example, start a counting semaphore with the value of 2, there can be at most 2 concurrent activities inside the critical section. Or you can take any other arbitrary number, and if you take the number 1, then you have something that is called a binary semaphore, which means that only 1 activity at a time maximum can be inside the critical section. Binary and counting semaphores are implemented in all major operating systems, so you have them available as primitives and can directly use them from your code. They are therefore also abstracted in higher level languages and libraries. When we again take the operating system look on the problem, one interesting aspect also already identified by Dijkstra is the busy wait problem. The wait operation in a semaphore is actually one that has to check data values and have to make sure that whenever something changes in the data value, if now the condition is fulfilled to enter the critical section. If you would do this in a stupid programming way, you could implement a so-called busy wait, where you loop over the content of the semaphore variable and check again and again if it now has the right value, because it may be modified by another activity that performs signal. This is a bad thing because busy waiting, cycling over the variable eats up CPU time without any good purpose. So Dijkstra already proposed to introduce a notion of sleeping, of putting the task to sleep when it calls wait. And this is something, again, we have to implement based on operating system mechanisms. So today in an operating system, if you use semaphore wait operations and the semaphore is not available for you, so it cannot enter the critical section, your thread of execution, your process of execution is put to sleep by the operating system scheduler until something changes. With this notion in mind, the Unix operating system families that fulfill the so-called POSIX specification for their API introduced another concept which is called a mutex. Mutex is an acronym for mutual exclusion, and it has similar behavior to a binary semaphore. It's not the same, that's very important, because it has an additional condition that changes the overall semantics, and this is the condition of ownership. A mutex is something that can be used like a binary semaphore, so you have a flag that protects your critical section so that at maximum 1 activity can be in there at the same time. But the second aspect here is that a mutex that is locked, so an activity locks a mutex in order to enter the section, can only be unlocked by the same activity. From a programmer point of view, from a protection point of view for critical section, this makes a lot of sense, and this somehow restricts the overall usage pattern of semaphores, where it may be possible to have different activities either calling the wait or signal function. So the idea of mutexes in modern operating systems is that this is the locking primitive that acts like you would expect from a binary semaphore concept, and it has additional conditions like the ownership condition that can prevent a couple of problems, especially in real-time operating systems. A mutex may support recursive locking. What is meant by this? Recursive locking means that you can call the lock function several times. If you do that without getting increasing counters like in the counting semaphore, you can start to avoid recursive deadlock problems that may happen if you have some programming error and unintentionally lock the mutex several times. The typical understanding today, if you look into programming handbooks and manuals and literature, is that if you want to do locking, protection of critical sections, you rely on the mutex concept that is given by your operating system. If you want to do signaling, or if you have a counting semaphore problem, then you rely on the semaphore concept. Here's an example for how locking could work based on the critical section idea and based on the concept of a mutex. So we have 3 different tasks here, task 1, 2, and 3. And we have progress of time from the top to the bottom. So task 1 starts with the demand to access the critical section that is common for all 3 tasks. So they share some kind of resource, and inside the critical section in each of these tasks they attempt to access this resource. So the first task tries to call the mutex lock function. Since the waiting queue for the mutex has no active entities, so there is nobody already waiting for entrance, also the mutex is not locked so far, the task can immediately enter the critical section. At some point in time, now task number 3 comes into the game in this concurrent execution and also wants to access the critical section. So it also performs a lock call on the shared mutex variable. In this case, the critical section is already blocked, so task number 3 cannot enter the critical section. This is here symbolized by the red block. In order to deal with that, the task 3 is now put into a waiting queue for this particular mutex and is put to sleep by the operating system. Time continues, and now task number 2 comes into the game and also tries to access the critical section, performing an according lock call. You see in the diagram now that at the same point in time in this scenario, task number 1 is doing the unlock call. And the interesting question is now, who wins first? We have task number 2 and task number 3 in the waiting queue, and who is now the one being woken up in order to access the critical section as the next one. And this depends on the kind of implementation you have. You see here that task number 3 gets a priority because he's first in the waiting queue, so he gets the critical section, and then after performing an unlock, the waiting queue only contains the waiting queue contains only task number 2, and after an unlock now the task number 2 is enabled to also enter the critical section. So this kind of synchronization game of concurrent activities is done by sharing synchronization variables like mutexes, and they protect the access to the critical section and the critical resources. If we now reconsider the deadlock problem we already identified and look on it from the semaphore perspective, the question is, can we still have deadlock problems with using semaphores or using mutexes? And the answer is yes, we can, no problem. And this relates to the fact that if we do either a semaphore wait or a mutex lock operation, we don't know how long it will block. So we have no real knowledge inside the code how long this situation will last. The second thing is we also don't know which of the activities will continue when we perform an unlock. So the interleaving of executions is not predictable from the pure usage of the mutex and the semaphore variables. And this is independent from the number of processing elements because this is a concurrency problem and not a parallelization problem. So we can have deadlocks in this situation. We also can have starvation situations. So although we are now able to implement the mutual exclusion demand and we are able to do mutual exclusion, we still may run into nasty problems of concurrency like deadlocks and live locks, depending on how we use the synchronization variables. You see here on the slide also an example where, depending on the interleaving of activities and the interaction with the resources, we may have a deadlock or not. So although we have protection mechanisms in order to share, to protect our shared resources, the wrong usage of this primitive still can lead us into synchronization issues and concurrency issues such as starvation and deadlock.